Now I want to solve the R programming problems from our lecture number 30 about joint continuous distributions and conditional distributions. So the first problem with R portion was the following. So we have this F, define it, joint PDF of X and Y, define it in the following way. So it is equal to 0.2 in the unit disk. It is some K in this rectangle and 0 otherwise. So the problem is to generate random points from this distribution in R. So we need to have the value of K to be able to do that. But first I want to talk a little bit about the method. And the method is called rejection sampling or acceptance rejection method, acceptance rejection sampling. So first about that method, but for the one-dimensional case, the idea is working for every dimensional case, but I want to explain it in the one-dimensional case. So what I want to do, assume that I have a function PDF, one-dimensional PDF. So this is PDF. F is non-zero in AB and 0 otherwise. So f of x is 0 otherwise if x is not in AB. So what we want to do, we want to generate random numbers from the distribution given by this PDF. So assume x is a random variable with this PDF. I want to have some random numbers, observations from this x, random numbers generated from that distribution. Say this is AB. We have this kind of graph for f. Say the area is 1 under that f. So this is f. Maybe I will write y is equal to f of x. And outside of that f is 0, so I will not consider everything else. So what I'm doing, what is that rejection sampling method? So first I'm taking some value m which is larger than all values of f. So this is m, and I'm drawing this rectangle. So with height m and base AB. So m is such that m is larger or equal than f of x for any x in AB. I'm taking any m in this way. So what next? I'm doing the following. I'm generating U, which is uniform. I know how to generate uniform one-dimensional numbers from AB. And then I'm generating V from uniform distribution with a uniform distribution from 0m. And I'm considering the points UV. So I'm getting some points UV. UV will be in this rectangle. Say UV can be here, UV can be here, UV can be here. And what I'm doing, I'm taking the value of x to be the value of u, given that v is less or equal than f of u. So what that means? Say for this point, this is my UV. This is my point UV. I'm not considering this because the value of v, this v, is larger than the value of f at that point. So uv, this is v. That is, in fact, I'm considering all points uv that will lie under the graph of y is equal to f of x, and I will take that point's first coordinates as my x. So this is the method called the rejection sampling method, and if I will generate this kind of axis, so I'm generating UVs here, and I'm taking only that use such that the that point is under that graph of f of x. In this case, the distribution of x will be exactly f of x. So this can be proven. Let me give just quickly the idea how to prove that that the distribution of that points x will be with PDF f of x. Say if I will calculate the following, say I want to calculate the probability that x is between, say, alpha and beta, given that y is less or equal than f of x. So I'm using this, but notation is x. Instead of u, I'm writing x, and instead of v, I'm using y. So I'm calculating this conditional probability. So this distribution of, I want to find the distribution of x. So I'm calculating the probability that it will be inside this interval alpha beta. So by the definition of conditional probability, this is the probability that x is between alpha and beta, and y is less or equal than f of x, and over the probability that y is less or equal than f of x. So what this will give? So geometrically, let us think geometrically. So what is this region? So this region is x is between alpha and beta, x is between alpha and beta, and y is less or equal than f of x means that I will have points here. So under the graph of f, and x is between alpha and beta. So I will have this array. So I'm calculating the probability that my point, not the array, sorry, not the array. So I'm calculating the probability that my point will be here. And that probability will be the following. So geometrically, because I'm generating from uniform distributions, geometrically that will be the array of these. Let me denote this by A. This set is A. So array of A over the total array of our omega, so in this case this rectangle. So the total array will be m times, this is height, m times b minus a. So this is the probability that my point will be in this region. Okay. Now, what is the probability that y will be less or equal than f of x? So that is the probability where my point will be here. So the probability that my point will be here, again geometrically, is the array of this over the total array. So in that case, I will have the array of this, and that array is 1, because this is the array under the PDF, and the array under the PDF is 1. So this yellow array, yellow marked array is 1, over the total array is m times b minus a. So in this case, I will have just the, I will have these two cancelled, and I will have the array of a, and the array of a is the integral from alpha to beta of f of x dx. So if I'm calculating the probability that x is between alpha and beta, conditional probability, this conditional probability is calculated by integrating f, then the conditional distribution of x, given that y is less or equal than f of x, this conditional distribution will have the PDF of f. If I'm calculating probabilities of being between alpha and beta by integrating some function between alpha and beta, then that means that that function is the PDF of that random variable. So the random variable x, given that taking only that values where y is less or equal than f of x will have the exact distribution f. So I want to write this method, by the way, works also for 2 dimensions, 3 dimensions, etc. So rejection sampling is very important tool for sampling. Well, it is not so effective. In fact, not the most well used, most important methods to generate random numbers. Why is that? Because we can have that to have 1000 points here, we are generating 1 million points, and all the points are outside of this region. So to obtain 1000, maybe we need to generate 1 million points in this rectangle. Well, that depends, of course, on the height of that m. If m is very close to the maximum or supremum of f, then we will not lose a lot of points. Well, that depends also on the shape of f, etc. In multi-dimensional case, we will have that this algorithm is not so effective, etc. So this is not the best method to generate, but this is one of the easiest methods to generate random numbers from given PDF in 1 dimensions, 2 dimensions, etc. So I'm erasing this, going back to, so I want to go back to our problem. So we have this problem. We need to calculate first k, then generate random points from that distribution in R by using rejection sampling. So k is calculated in the following way. So the value of k is the integral of f over the total R2 needs to be 1. So the volume under this is 1. So that volume under f consists of 2 volumes: the volume of a cylinder with height 0.2 and the basis of basis unit disk, the area is pi, then plus k times the area of this rectangle, which is 2. So this is equal to 1. So k is equal to 1 minus 0.2 pi. We have obtained this value over 2 in our lecture. So I will use this value of k. So what I'm doing, I'm moving to R and doing rejection sampling for this. First defining my function f, then generating, in fact, because we are talking about 2-dimensional joint PDFs, 2-dimensional case, I need to use three variables. So u will be uniform. This will be for x. This will be uniform from, well, I need to cover all possible cases. So I have 2 portions, -1 to 1 and 2, 3 to 3. I have rectangle here. So x is from -1 to 3. So -1, sorry, from -1 to 3. V is for y, and that will be uniform. So y is running, this is -1, and this was 4. This is 4, yeah. So u is minimal -1 and maximal 4, so uniform from -1 to 4. And what about w? W will run, this is the m I was talking about for 1-dimensional case, the larger than the maximum value of our f, and the maximum value, well, it can be equal also. U will be uniform from 0 to the maximum value of f is, well, either this k or 0.2. Yeah. 0.1, let me see which one is larger. So 0.2 times 3, 0.6 with something, 1 minus 0.6, 0.4 over 2, 0.1. So this is larger. So maximum value is 0.2, so I can take 0.2. So I will generate 3 numbers, u will w, and I will choose that point u, v as my xy if w will be less or equal than the value of f at that point u, v. If this will hold, then I will take that value. Otherwise, I will not take that value. Okay, so I'm doing these calculations in R, first defining my function f. So I'm erasing this, going to R and writing here. So my function f, function of two variables x and y, define it in the following way. So if x squared plus y squared is less or equal than 1, then return 0.2. The value was 0.2. Else, well, else if x was between 2 and 3, so if x is, let me take another parenthesis, if x is larger or equal than 2 and x is less or equal than 3, and I am copying this and making that for y. So if y is larger than 2 and y is less than 4, in this case y is less than 4, then in that case I'm return that value of k, and k was 1 minus 0.2 times pi and over 2, and I need to add something like this. Else return 0. Okay, so I'm running this function, running this part of code. Let me check, say f at the point 0, 0 at the origin. So f is 0.2. Yeah. So one thing, well, maybe wrong with this f is that I cannot put many values of f. So I cannot straightforwardly calculate the value of f for vector, so pair of vectors, or vector of pairs maybe. To that end, to be able to work with vectors, I am doing vectorizing that function, so it is easy in R. So I'm writing vectorize my f. I'm running this. Now I can calculate the value of f at some vector. Well, I will do that. So you will see the result. Now what I'm doing is the following. So I need to generate, so my u is R uniform. First I'm taking how many points I will generate, say n is 1000, say, running this. I'm generating uniform n points from -1 to 3. This is for x. I'm generating v for y, again uniform, and numbers, and from -1 to 4. I'm running this, and I'm generating w for the height, runif for rejection sampling method, runif, again, and numbers from 0 to 0.2, the maximum value of our f. So I'm running this, so I have all these numbers. So what I'm doing, I need to choose from u and v all that points such that w is less than the value of f at that point. So what I'm doing is the following. X is from u, I'm choosing all elements, all elements such that w is less or equal than f at uv. So this is a conditional operator, so this will be either false or true. If we will have true, then that element of u will be recorded in x, right, written in x. If this is false, that will not be recorded. So x will be the portion of u such that w is satisfying this inequality. So here in f, u and v are 1000 dimensional vectors. You can see u is 1000 dimensional vector. So inside of f I am writing uv. So that will work because I have vectorized that my f. So I'm running this. So I have only 264 points lying here. So I'm doing the same for y. So I'm copying this. And here I will write y is equal to, and I'm choosing from v with the same condition. I will choose u and v coordinates for all points that satisfy w is less or equal than that. So I'm running this again, Control Enter, hitting, and now I have that point. And now I am drawing that points, plot x and y. Point character, I will do that with 19, and the size of character, let me take a little bit smaller than ordinary size. So I'm running this. Yeah, I have this kind of thing. Well, I need to keep the aspect ratio, so I can add ASP is 1, so aspect ratio is 1. So I will have this kind of graph. So let's see what will show that. If it will show, I will do the same. Yeah, so I have points here generated and I have points here generated. I will increase the number. I have just 264 numbers, so I have generated 1000, only 264 were successful for me. What I want to do, I want to use ggplot. Well, sometimes I'm using ggplot for my graphics in these slides. So I'm using that library ggplot 2. Yeah, I'm running this. So now I can use all functions from that library. I have imported that library. So what I'm doing the following. Say I am opening an empty ggplot. Yeah. Then, well, yeah. Now I can do the following. G plus. I'm adding elements in ggplot one by one. So I'm adding geometry points, point. I'm writing aesthetics. I want to draw the point x, y, so I'm writing that point. Let me run this. So, and you can see the, yeah. So I want to keep the aspect ratio, so I'm adding to that. Well, I can add it here. So chord fixed. So I'm fixing coordinates. So this is that graph of points. Now if I will increase the number, so what I'm doing, I'm taking 50,000 points. I'm running this portion. I will draw with ggplot. So I'm running this. So in this case, out of that 50,000, only 12,000 are satisfying that condition. Now I will run this and see the picture. Yeah. I have points distributed by according to that probability. Well, more points maybe here than there because the height was higher here. Okay. So this was for the first problem. For this problem, I have generated random points from the distribution. And the second problem was asking to do this. So this is our joint PDF. Define it on 0, 1, 1, 2, and 0 otherwise. It is in this form. So in the next slide, let me show that next slide. Yeah, I have generated points, and this is in ggplot. So let me obtain this by using R. So I need to, I will do the same for this. First, I need to generate 3 uniform random numbers. So for x, my x is changing from 0 to 1. So I will generate u from 0 to 1, v from 1 to 2, and w I need to take from 0 to some kind of maximum of that, or something that is larger than that maximum. But effective is when we are taking something close to or exactly maximum. So x, the largest value of x can be 1, the largest value of y can be 2. So the largest value of this will be 4 times 2, 8. So the largest value of this will be 1 plus 8 over 3, that is 3. So I will generate w from 0 to 3 uniformly. And then pick all u and v's as x and y for which w is less or equal than the function value at uv. So I'm doing that rejection sampling for this case. So what I'm doing, I'm changing my function. So changing my function, no need for this. Okay. So my function will be if x is between 0 and 1, so x is larger than 0 and x is less or equal than 1, or y is from, well, y was from 1 to 2, so 1 to 2. Yeah, return, the value was 1 over 3 times, so sorry, I need to erase this, 1 plus 1 plus 4 times x squared times y. Yeah, over 3, and otherwise return 0. So I'm running this, then vectorizing, then generating. I need to change these values, so I'm generating from 0 to 1 for x, from 1 to 2 for y, from 1 to 2 for y, and from 0 to maximum 3 for z. So u, v, w, and I'm choosing all points as x and y such that the w's are under that surface. So running this, running that. Now I will do not the standard plot but ggplot. So opening new ggplot, then adding that points. Yeah, maybe I will decrease the values. Maybe I will use 10,000 and run all this. Well, I have obtained that picture without fixing coordinates, without having this. So let me try to obtain the same figure. Yeah, this was what I have obtained. Most of the points are here at the corner. So this was how I've obtained this. Well, the size of my points were, maybe I will add cx is equal to 0.0, say maybe 7, Let me run this. Yeah, something like this. Okay, so the next problem was the 57. Yeah, so this was about conditional distribution. So let me just recall what we have obtained for this case. So for this case, we have obtained the following. So marginal PDF of x was f of x was 2 over pi times square root of 1 minus x squared if x is between -1 and 1, and 0 otherwise if x is not in that interval, -1 and 1. And the conditional distribution of y was, well, recall the picture. This was the picture. This is -1, 1. Our f is non-zero here, k. In fact, that value of k is 2 over pi. If x is here, then y was conditional distribution of y over this line. In fact, the distribution of y over this line was uniform. So y given x is equal to x is uniform in 0 to this point, and that point is square root of 1 minus x squared. So what I want to do, I want to generate a random sample, random variate from this distribution in R. So points here with this distribution. How I will obtain? So first I will generate values x from this distribution, and for that I will use rejection sampling. So I will obtain some points with this distribution. Then for each point I will generate a uniform number from 0 to that square root of 1 minus that point squared, and return the point xy. So I'm doing this in R, erasing and passing to R. I will open a new R script. Yeah. So first I'm defining my f to do that rejection sampling. So this is a function of one variable x. Define it in the following way. If my x is between -1 and 1, so let me write x squared is less or equal than 1, then return what to return 2 over pi 2 times square root of sorry, something's wrong. Square root of, yeah, maybe I need to close because it is changing something. Yeah, I'm sure, no need for that. Square root of 1 minus x squared over pi, otherwise else return 0. So I'm running this code. Yeah, so let me check. F at 0 is, well, something. Yeah, f at 10 is, yeah, 0. Nice. So I need to vectorize. Say what I was saying. If I will run this for 0 to for this vector, well, that is giving, well, in fact it is calculating and giving error. So let me vectorize this. If I will write vectorize f. I have vectorized that. So I'm generating UV. This is one dimensional. So I will take two values, u and v. So u is R unif. This is for x. So how many points I need to have? Let me use n again, say 1000. R unif, I want to have n points from uniform from -1 to 1. So x is between -1 and 1. V is from 0 to m. M is the maximum, and the maximum value of this will be at the point when x is 0, so 1 minus x squared, maximum is when x is 0, and the maximum will be 2 over pi. So I will generate uniform numbers from uniform n numbers from 0 to 2 over pi. Okay, and I will choose only for x, I will choose only that points from u such that v is less or equal than f at the point u. So I'm running this. So out of that 1000 u's, only 787 were under that curve f of x. So I have now generated x from my distribution. Now for each x, I need to generate a uniform number from 0 to square root of 1 minus that x squared. Unfortunately, I cannot write in this way. So if I write r unif, say how many elements I need to have, say 10 elements from 0 to square root of 1 minus x squared. Say I'm running this. Yeah, so this is not generating for all values of x. Here x is a vector, so I need to do something for this x. So what I'm doing is the following. Let me just check if that is working. Say, let me generate y is r unif, well, 10 from 0 to 1 to 10, something like this, and print the values of y. Yeah. Well, that is generating some numbers. Well, can we be sure that that is generating that correctly? Okay, I will do this way. I know that this is working. So what I want to do, I'm doing the following. So I can use the following command list apply, or the following. So apply that for all x. So apply that for all x. And what I'm writing here, I'm writing what function to apply for all x. So function of function, I'm writing a function here, function of say t, and that function will work like this. Return r uniform, just 1 point from 0 to square root of 1 minus t squared. So this function, this inner function, I could write that separately. What is doing this function? It is returning just 1 point from the uniform from 0 to square root of 1 minus t squared. And I'm giving t to that function. It is returning a random number from 0 to square root of 1 minus t squared. And I'm applying that to this list to x, and I'm keeping the result in y, so I'm running this. Okay, now I have x and y. I can plot that point, so to see if everything is correct. So I will do that in ggplot. So I'm opening new plot, ggplot. Yeah, I'm running this, and then adding to g that jump point, not points, point with aesthetics using x and y, and let me use cx is equal to 0.8 and fixed coordinates to have nice graph. So I'm running this. discrete points are, oh, yeah, what is wrong here? So let me see what is why. So if I will do that in ordinary plot, so plot x, y, let's see if this is working. Yeah, this is working. So okay, so I am adding this and running that. Yeah, I have that point. So if I will increase it 10,000, sorry, I'm choosing, applying, this is returning a list. That was the problem. So I'm making a numerical vector and then plotting that points. Let's see if that will plot the points. Yeah. So this is the distribution obtained by using conditional distributions. So first, you can see, by the way, that the density everywhere is the same. So this is uniform distribution on that half circle. Uniform distribution on that half circle. So this much. Thank you. Bye.